Okay, our last example then is, as you can see what I call here, instead of a classic calculus question, this is a classic vector question. What we have is a sign with mass 50 kilograms is suspended as shown. Find the tension forces in each wire. So you've got a ceiling that's outlined by these lovely dashes, and you've got a sign which is 50 kilograms, and you have two wires. One that's a little bit shorter at an angle of 60 degrees, and another one that's a little bit longer at an angle that's 45 degrees. What's important is for you to understand that this is the actual picture. We're going to draw a vector diagram of this scenario in a moment. So again, if you need some more time to copy it down, just ask the teacher to pause, but I'm going to move on. So what our job is to find the tension forces in each wire. So first off, let's talk about what force is being applied. Well, the sign here has a really strong force being pulled on it. And it is, of course, the force due to gravity. And that is some vector that's down here. There's a quick little way to find that force due to gravity. And for those of you who've taken physics, you probably know this. But the force due to gravity can be found by taking the mass times a constant for gravity. In this particular example, it is 50, and we have to do it in kilograms. And our constant, and most of you are probably screaming at the board, the constant is 9.8. It's actually a little bit different, a longer decimal than that, but for our purposes, we'll use the gravitational constant as 9.8. And if we do 50 times 9.8, we get then the force due to gravity is 490 newtons. Now, the next thing to understand is that this sign is in rest, which means it's not moving around. The tension in the wire is holding the sign in place. So there's a combination of two vectors that are the tension vectors that are holding this in place. And it's important that we see its direction. We know that there's a vector right here. We don't know how long it is. It's not the same length as the rope. Remember, this vector is a representation of the tension, not how long it is. But I'm going to call that vector T1. And then there's a second vector up in this direction. Again, it could be bigger or smaller, and you might be able to predict whether it's going to be bigger or smaller. It's tension 2. And these vectors, they could have been drawn way outside the lines. We're just getting an idea of the vector representation of this real-life scenario. Those two vectors have to combine to get some sort of resultant that is exactly the same as the force due to gravity, but in the opposite direction. So when we add these up, we should get some vector that's that. And this one should be 490 newtons. If this is 490 newtons, exactly, then the sign is in place, and it's not moving, and it's in balance. So we need to use the sum of T1 and T2 and hope that it results in a vector that's 490 newtons going straight up, because it has to counterbalance the 490 newtons of gravity that is pulling it straight down. Next comes taking the picture and drawing a vector diagram. Okay, so this is our vector, our vector diagram. So let's take these scenarios. We know that we have to produce a vector that's going straight up. So let's draw this. And this one has to be 490 newtons. And we're going to need T1 and T2 to result in that. So let's make that one blue just so it looks like a picture. So T1 is going to be right here. And we're not sure exactly how long it is. It's going to be roughly here. But remember, this is a sketch of a possible scenario. So I'm going to draw it about there. And then T2 is going to go right there. And we'll see that this is T1 and this is T2. And my picture here might have to be a little bit longer, but again, that's not the point. The point is we have these two possible representations. We don't know how long they are, so we can't draw an accurate picture. But we know that when we add T1 and T2, it has to come to a total of 490 in that direction. Remember, it's not going to be like this is 200 and this is 290, and that gets you 490. If they were in the same direction, it would be 290 and 200. In this case, it's going to be something bigger and bigger to get a result of 490 going straight up. Probably the most challenging part of this question is the next step, coming up with the angles. Because we can't use the cosine law here, we don't know enough information. We're going to have to use the sine law in both cases to get T1 and T2. So we need a lot more angles. So to fill in the angles in our vector diagram, we're going to have to go back to our actual picture. And I find that this little strategy works. It's one of the reasons why I wanted to do a video lesson here, so you could see this instead of just reading it off of Moodle. So first, let's try and replicate 45 degrees. 45 degrees is this angle right here. And I'm going to trace it a couple of times to really get it in my head. You'll notice that I'm going along T1 and then a horizontal. T1 horizontal, T1 horizontal, T1 horizontal is 45 degrees. So where is that in my picture? Well, there it is, T1 and horizontal. See that? T1 horizontal 45, T1 horizontal is 45 degrees. The 60 degrees is over here. And I'm going to draw it a few times, say it in my head. It's going T2 and then backwards, isn't it? T2 and backwards, T2 and backwards, along the horizontal, T2 and backwards is 60. The end of T2 and coming back this way. So if I go to my vector diagram, there it is, T2, and then backwards to horizontal, that's 60 degrees. Getting those in the right spot is extremely important. The most common mistake I see is that people say, this is 60 and this is 45. This one might be 45, but this one's definitely not 60. And don't just throw them in willy-nilly. You really have to make sure you know where those angles are. Once you have those two in place, the rest is some of the math we already know. If this is 60 degrees, then we know that 90 minus 60 is 30, so that one in there is 30. We also can use the Z pattern to say that there's 60 horizontal come along here, and another horizontal, which makes this 60. The same argument can be used over here to get the 45. So there's 45, which 90 minus 45 is 45 there. That's just happened because it was 45. If this was 40, of course, that wouldn't work. But you'll now notice that I've got, there's 30, there's 45, and these two add together to 105. And I have all the angles necessary in my diagram to solve for T1 and T2. So let's do it. Let's solve for T1, for example. So since I'm going to use the sine law again, but I'm going to write down my unknown. In this case, it's T1. So T1 is what I don't know. And I'm actually going to put the absolute value over there because right now I'm only calculating the magnitude. Okay, you could just put T1, that'd be okay, but later on, understand this is just the magnitude. And it's the sine law, so it's T1 over its opposite side, or opposite angle, excuse me. So I'll go to red here just to make sure I see that there's the opposite angle. So it's T1 over sine 30 degrees. And it equals, and now I need two sides that I know to compare it to. And that's where I know these two pairs. I know the 490 and the 105 degree angle. So it's equal to 490 is on the top this time, and the sine of 105 is there. Now I'm going to solve for T1. The reason I put T1 up there is so that my math is relatively easy. in that I just need to, since it's being divided by sine 30, I'll multiply, so it'll be 490 sine 30 degrees over sine 150. Punch that in my calculator, and I'll give you a second if you want, but the answer should be 253.6 newtons. So I'll very quickly solve for T2 doing the exact same method. Just make some space here. This is going to be T2, magnitude of T2, and its opposite angle is 45, so sine 45 equals, and I can compare it to the same thing, 490 over sine 105. Dot, dot. Multiply by sine 45, get an answer, and T2, it turns out, is 358.7 newtons. And if you'd like to pause right now to double check those numbers, you can. Let's do a quick check to see if this makes sense. Remember, we didn't think that it would just be this number plus this number and add it up to 490 because they're in opposite directions. So it does make sense that the numbers, when you add them up, are closer to 600 because you will need more force in T1 and T2 to counterbalance the 490 straight up. And we'll just finish then, since this is a word problem, we'll finish with some actual words. So therefore the tension in the cables are 253.6 newtons and 358.7 newtons respectively. Couple of words of advice. Really make sure that your picture is nice and big so that you can see it all. You can see how very easily it is to get a little messy in there, and you'd hate to make a little bit of a mistake because you misread some of your messy numbers. Notice that you're going to draw a actual picture and then a vector diagram that's necessary in both, but that the math itself isn't too difficult once we get down to it. The challenge in all these questions is definitely coming up with this picture. I have full confidence that you can do all the math. So that's it for now. Remember that the copies of these printouts are on the Smartboard lessons right now, or you can go to Moodle and get the exact ones for you to check and see if you missed any of those part of this lesson. But hopefully this has been helpful. Thanks very much. See you tomorrow.